The transport of macromolecules and particles within porous media and polymeric networks is a fundamental process in various natural and engineered systems, including soil filtration, drug delivery, tissue engineering, and water purification. In these environments, the movement of large molecules, or colloidal particles, is governed by a combination of mechanisms such as diffusion, advection, and, in some cases, active transport. Porous media are characterized by a complex network of interconnected voids, or pores, whose size, distribution, and connectivity significantly influence the transport properties. Macromolecules and particles often encounter physical hindrances due to pore constriction, tortuosity, and potential adsorption onto the pore walls. The effective diffusivity of these species is typically much lower than in free solution, as their motion is restricted not only by geometric confinement, but also by possible interactions with the matrix, such as electrostatic attraction or hydrophobic effects. In polymeric networks, such as hydrogels or extracellular matrices, the mesh size, defined by the average distance between polymer chains, plays a critical role in determining the mobility of solutes. When the size of the macromolecule or particle approaches or exceeds the mesh size, steric exclusion becomes significant, leading to size-selective transport. Furthermore, the viscoelastic nature of polymeric networks can impart time-dependent resistance to motion, sometimes resulting in anomalous diffusion behavior where the mean-squared displacement of particles deviates from linearity over time. Transport in both porous media and polymeric networks is further complicated by dynamic changes in the environment, such as swelling, degradation, or restructuring of the matrix, which can alter pore or mesh dimensions over time. Understanding and modeling these processes require integrating principles from fluid dynamics, statistical mechanics, and materials science, often employing advanced imaging and tracking techniques to elucidate the pathways and rates of transport at micro and nanoscales. Overall, the interplay between molecular size, matrix architecture, and physicochemical interactions defines the efficiency and selectivity of macromolecular and particulate transport in these complex systems, with direct implications for the design of materials and devices in biotechnology, medicine, and environmental engineering.